Nikhilesh, we can start now.
Okay, Akhilesh, thanks. So, hello everyone. Good morning, good afternoon, good evening. Let me introduce myself. I am Nikhilesh Mehta. I am part of NCS 1K test team. So, today's session is about how are we achieving high capacity in optical communication system. So, let's start. Let me go through the agenda of today's session. So there are two parts in this presentation. In the first part, I will talk about the coherent technology, the basics behind the coherent detection, the advantages of using the coherent detection, and why there was no coherent detection before, and how can we achieve the higher capacity in optical communication. And in the second part, I will talk about how we are leveraging this different technologies in our NCS 1K platform, where we are how we are outperforming from our competitors using these platforms. And I will also talk about the submarine use case using the NCS 1004. So let me start with the basics. So this slide is about what's the difference between the bit rates and baud rates. So this terminology we comes very often, the baud rate. So the bit rate is defined in terms of number of bits you send in per second. So if you see here, there are 8 bits, and if you take a chunks of multiple bits, in this case 2 bits if we take, then they are the symbols. And if we send those symbols, then I'll call it as a symbols transmitted per second, and that is not nothing but your baud rate. So the key point is symbol rate or baud rate describes the symbols transmission instead of bit. So the clock rate, not the transmission data clock rate. So this is the difference between bit rate and baud rate. Now coming to the coherent detection. So the in the coherent detection, we have the local at the receiver, and you can see there is a local oscillator which is being mixed with your incoming signal, and then you receive the signal. You have the photodetectors, demodulators, and then decision circuit. So here the important thing, prior to coherent detection, you had a on-off key. So the decision were based on whether you have a signal or you don't have the signal. That means only on the basis of the amplitude of the signal. But after the coherent detection, using this technology, the phase part is also coming into the picture. So if you see here, the signal field plus the local oscillator field, when you mix it, you get the signal plus local oscillator, plus there is another term which comes, which is amplitude plus the phase of the signal. That is also very important. So we can say that the coherent detection is sensitive to the phase of the light as well as the amplitude of the light. Now, what are the advantage of using the coherent detection? Some of the advantages, like you get a better optical gain. The other thing is only the light in close neighborhood of local oscillator wavelength is seen by coherent detection. So it also acts as a ultra narrow WDM filter. What I meant here is, if any particular wavelength you want to receive, then you can tune your local oscillator around that filter, and you will be able to receive only that wavelength. So if any other wavelength comes, the receiver doesn't detect it. The third thing is the phase encoded modulation format can be detected. So you might have heard going to the higher modulation format like BPSK, QPSK, QM modulation. So all these are possible because of coherent detection only. In our further slides, we'll talk more on these higher modulation formats. So going further, why there was no coherent detection before? One reason is the receiver becomes more complex. So you can understand that you have to use the local oscillator. The decision circuitry becomes more complex. The DSPs which we are using at the receiver, that becomes more complex. So this was one of the reason we were not using the coherent detection before. The other things are, to get the best sensitivity and detect high bitrate signals, the phase of the local oscillator needs to be logged with the incoming signal. So that local oscillator should have that intelligence that So had should have the feedback mechanism so that it can lock the it's a phase with the incoming signal. The other things are like polarization management needed to match the state of polarization of local oscillator to incoming signal. So the polarization should also be matching. And to achieve the best sensitivity, synchronous detection is needed. So all the points are around uh, the synchronizing with your local oscillator. So this was not possible before, but now we have the faster sampling possible and we have the faster DSP availability. That's why we are able to achieve this coherent detection. So, going forward, how can we achieve the higher capacity? What are the different ways we have in the optical communication systems so that by the virtue of which we can achieve the higher capacity? These are the different ways. You can have time division multiplexing, you can have wavelength division multiplexing, you can go to the higher modulation formats, you have the polarization division multiplexing, and you have the spatial division multiplexing. These are different ways. So in the subsequent slides, we will see each points in detail that how we are achieving that. So coming to the time division multiplexing. So if you can see here, you have multiple data streams C1, C2, C3, C4. So each data stream is, you can say it's each of 10 gigabit per second, each data stream. So if we want to multiplex this, so in the time domain, if we are multiplexing, then we will take a single bit from each data stream and then send it. So you can see at the after the multiplexer, you have C1, C2, C3, C4, a single bit from all the data stream, then again the second bit of C1, C2, C3, C4, and so on. So what we have achieved is the input individual C1, C2, which was of 10 Gbps. After the multiplexer, you are able to achieve 40 Gbps electrical data stream. But what we will need is more bandwidth in this case, and the power requirement will also be more. So the commercially available transceivers are modulated at up to 70 gigabaud per second. This is what time division multiplexing is. Multiplexing. Then we go to the wavelength division multiplexing. So in the wavelength division multiplexing, instead of multiplexing the signal in the time domain, what we are doing is we have the spectrum of different wavelengths. So we are sending my different channels at different wavelength. So as you can see here, we have the laser plus modulator 1, modulator 2, and there are multiple modulators. So each channel I'm modulating at different frequency, or you can say at different wavelength, and then I'm multiplexing it and I'm sending over a fiber. And at the receiver, I will use the demultiplexer to demultiplex all those wavelength, and I will receive them so that all the individual wavelength I will receive separately, and I can send more data with higher capacity in the fiber. So you can see in this example, uh, there are 120 channels I'm sending here, and each channel is having a speed of 25 Gbps. So the total capacity will become 120 multiplied by 25 Gbps. So total capacity of this will be 3 Tbps. So using the wavelength division multiplexing, I am achieving the higher speed in this case. Now coming to the polarization division multiplexing. So till now we have seen time division multiplexing, wavelength division multiplexing. Now this one is how you can use the polarization of the wave to achieve the higher capacity. So as you know, as you know that a light have the X polarization and the Y polarization. If you use the polarized and send a unpolarized light through the polarized, then what at the output you will get a light uh, with a polarization in a single axis, single direction. So you can see there is a polarization splitter which is being used here. So you have the X polarization light, and then you have the Y polarization light, and you are modulating those two signals separately, and then again you are combining it using the polarization combiner, and after that you are sending it through the fiber. And at the receiver you are demultiplexing it, and then you are receiving at the Rx1 you are receiving the X polarization, and at the Rx2 you are using the Y polarization. So what we have achieved is, instead of sending a light with single polarization, I am sending on two different polarization, so the capacity will be doubled in this case. So what it says is optical polarization division multiplexing is based on transmitting independently modulated signals over orthogonal polarization of the same optical wavelength. The use of PDM permits multiplying the transmission capacity, as different signals can be transmitted over orthogonal states of polarization of the same light. So this is how you can achieve the double the capacity using the polarization division multiplexing. At the end of the slide in the part 2, we will see how all these different technologies we are using in our NCS1K as well. So applications of this technology. Now this one is how you are using the higher modulation formats in the optical networks. So instead of using on-off king before, we use MPSK and MQM. So coming to the what is digital vector modulation. So as you see here, the sinusoidal wave, each point on this wave is represented by some phase. So this, for example, this point is of 90-degree phase. This point is of 150-degree phase. And if I plot this all the points around a circle, so you can see you will get a circular trajectory, and the difference between any two wave that will be defined with the help of phase difference. So the phase difference is the difference between the two waves having the same frequency and reference to the same point in time. Now, how I'm utilizing this particular thing is, for example, any point on the circle that can be represented by its phase value and its amplitude value. So that we also represent by I and Q. I is the in phase, and Q is quadrature phase. So what it says is every carrier signal can be described with two parameters, either amplitude and phase, or it's also we can say in phase and quadrature phase. So both the parameters can be modulated to carry the information. So this is what coherent detection has helped. Before the coherent detection, it was not possible. But since using the phase difference technology, we are able to use this. So how we are sending the symbols by the modulation. So as you see here, this first one is your data clock, then you have the I phase and you have the Q phase. So if you see two different symbols which are 180-degree apart, so this symbol is 10 and this symbol is 11. So how the 10 is represented uh, is using this I component, and then you have the uh, this 11 is the first one of both the symbols is your I component, that is your this green one, and then you have the Q component, that is your this brown one. So now when I combine the I and Q, this is what the transmitted signal you get, and you transmit this signal instead of sending them individually, so that at the receiver you will get the, and then using the DXP at the receiver you can see what is I component and Q component, and then uh, you can demodulate your signal. So this is the example for your PSK modulation. So like BPSK, QPSK, MPSK. So at the input, you have a bit stream of 11000110. This is your binary bit stream. So what you are doing is you are demultiplexing. So if you see in this leg, you have 1001, and in this leg, you have the 1011, 1010, and then you are using the Mach-Zehnder modulator. So what is Mach-Zehnder modulator is, you are the two legs are pi by 2 phase apart. So the first leg, the upper leg will be your I component, and the below leg, which is pi by 2 apart, that is your Q component. And the original signal which I will transmit is the addition of I and Q. So if you see here, the I and Q addition, 1 1 will be like this, 0 0 will be like this, 0 1 will be like this, and 1 0 will be like this. So the signal which will be transmitted will be your the addition of I and Q, which will be this one. So this is also known as your constellation map, where you are representing each carrier as a symbol. So you can see this 0 1 can be represented by this symbol, 1 1 can be represented by this symbol, and all the points are pi by 2 phase apart. This will be the constellation map for your QPSK. So now coming to the QAM modulation. So in the QPSK, I playing around with the phase of the signal, not the amplitude. You can see in this, the amplitude of all the carrier, all the points are same, all are lying on a circle. But in the QAM modulation, you are also playing around with the amplitude as well. So this is quadrature amplitude modulation. Your phase may also change, your amplitude might also change. So in this is the example for you of your 16 QAM amplitude modulation. So you can see there are 16 points in the model in this constellation map, and each points. So if you have to represent 16 points using the binary, then you will need 4 bits. So that means is we are sending 4 bits per symbol. So here. This was the example for 16 QAM, and this is the example for your 64 QAM, where you are using, instead of 4 bits, you are using 6 bits. So the problem which comes is, as you as you keep increasing the number of bits, going to the higher modulation higher modulation format, this points, the distance between the 2 points, that keeps reducing, and then we will not be able to differentiate between the 2 points because of the noise in the system. So this is what it says: the more number of symbols, the less the system is resilient to noise. This is what the problem we face when we go to the higher modulation format. Now, we talked about the higher modulation format. So till now we talked about the TDM, WDM, polarization division multiplexing, higher modulation format, and this last one is about the spatial division multiplexing. So till now, whatever we discussed, that was controlled using the DSP in the system. But the spatial division multiplexing, this is more like a physical phenomena. For example, to increase the transport capacity in a single cable of the fiber, you are using the multiple fibers. Like we use in the Wi-Fi, you send the signals in the multiple direction, and at the receiver, we use the MIMO to receive all those signals. Similarly, here we use the multiple fibers and send different signals via different fibers, and at the receiver, we might combine it at the receiver. We You can use multi-fiber. The second option is you can use multi-core. What is the meaning of this is, in a single fiber, it's different kind of fiber where you have a multiple core in a fiber, and you send different signals via different core, and at the receiver you differentiate those signals. The third one is your multi-mode. Generally, for long distance, we don't prefer it. We have the single mode fiber, but for the shorter distance, you can use a multi-mode fiber, where you are, as you can see in this diagram, you have a multiple modes, which are at the receiver. You can differentiate between these different modes, and you can differentiate between the signal, and you can achieve the high speed. So the conclusion here is, so we can play with any attribute. We have the different options to increase the transport capacity. One thing will depend on might depend on the other, but you have the multiple options. Like you have the time division multiplexing, polarization division multiplexing, space division multiplexing, frequency or wavelength division multiplexing, and then higher modulation format. You can combine all of them. It's not like you use only one thing, but you have the uh, you use the technology in different way. that in that so that you can achieve the higher capacity. So if you see in this example, the total capacity is the multiplication of everything. You have the number of NB due to spatial mode, NB due to polarization, NB due to wavelength, NB due to bits per symbol, and symbol rate or baud rate per overhead. So this is what the total capacity you will get by multiplication due to all the phenomena. So if you see the example, there are 120 channels. You are using the PDM, polarization division multiplexing, with 16 QAM, and each channel is represented using the having the 25 gig information symbol per second. So the total capacity will be 120 into 2 due to polarization division multiplexing into 4 due to 16 QAM into 25 gig. So that will come out to be 24 Tbps into number of fibers due to spatial division multiplexing. So this will be your total capacity in the fiber. So so can we keep increasing? So by using different by playing with different attributes, is it possible that if we can keep increasing the speed in the optical communication? The answer is no, we cannot keep increasing. There is a limit for that, and there was a paper in which Shannon has given this paper. He has given this limit. This is a theoretical maximum data rate limit. So this is defined for all the communication channels, not only fiber optical channels, but all the channels. What this Shannon limit says is, he has given one formula, that is C equals to B log to 1 plus S by N, where S by N is your signal to noise ratio, B is your bandwidth of the channel, and C is the channel capacity. So what this graph represent is, you cannot have keeping the same signal to noise ratio, you cannot keep increasing the bits per symbol. Uh, you need to have the better overhead so that you can achieve the good BER value, that is bit error rate, bit error rate. Otherwise, what will happen if you increase the bits per symbol? As I said, the noise will increase in the system, and because of that, your BER, you will not have a good BER. So you will not, the receiver will not be able to detect the signal. Uh, you will not be able to detect the signal. So this is the theoretical limit given by Shannon. Now coming to the coherent optical development, what are the development we have so far in last 10 years? So as you see, we moved 100 gig to 800 gig per optical channel in last 10 years. In 2010, the first solution which came was 100 gig coherent solution, which was QPSK, and we were using 32 gigabaud. We were able to use 32 gigabaud QPSK, and so we were able, using this, we were able to achieve 8 Tbps using the C-band DWDM using the complete spectrum. Now in 2013-14, 200 gig coherent came. Then in 2014, 400 gig came. So it was more flexible. You were able to use 100 gig, 200 gig, 300 gig, and 400 gig flex rate. And there were different solutions for this, like CFP to DCO, OSFP, QSFP DD, which is coming in 2020. So these are different solutions which uses 400 gig coherent technology. Then 600 gig coherent technology, which came in 2017. In 600 gig coherent technology, we use 64 gigabaud with 64 QAM. And as you can see, in 100 gig coherent, we were getting 8 Tbps in the fiber. In 600 gig coherent, we are able to get 38.4 Tbps using the C-band DWDM, 64 channels with 75 gigahertz spacing. Uh, and if we use in this C plus L band, we are able to get 76.8 Tbps, which is huge in a fiber. Uh, and then the final one is the 800 gig coherent, which is coming in 2020, the first solution for DCI in 2019 and 20. In this, we are using 90 gigabaud with 64 QAM. And at the research level, even the capacity which we are able to get at the research level, that is even more, where they are using 128 gigabaud and higher modulation formats. So this is the total development which we had in the coherent optical field. Now we will move to the second part of the presentation. Let me know if there is any questions till now. Am I audible? Just confirming.
Yes, Nikhilesh, you're on.
Okay, Akhilesh. Then I will move to the second part of the presentation. That is how we are leveraging all those different technologies, coherent technologies, and making our NCS 1004 and future platforms and differentiating with the competitors. So this is the NCS 4. So what we are able to achieve in this I think it's NCS 1004 came in 2019 only, and we are the DSP which we are achieving here, it's more compact, higher density. Instead of 28 nanometer, we are able to achieve 16 nanometer DSP. The modulation format is we are moving from 16 QAM to 64 QAM, and the best part is we are also able to achieve the hybrid modulation. Then we have the higher baud rate here, instead of using, so we have the flexible baud rate, we can play around with the baud rate, and we have the line rate encryption. So this, since it's a very flexible platform, you can play around with the many things. It's very universal as well, for in the different segment of the different segment this platform can go. It can go in the metro market, long haul market, and subsea market. Google is using this platform extensively in the subsea market. So as you see, it's a truly flexible metro to ultra long haul, 50 gig capacity increment. So and fixed grid as well as flex grid, both are possible in this. Now going forward, this is the default trunk rate which are possible in the in the Boss Hog. So this is just a very a small list. What we can have is a very extensive list of values which you can configure in the platform as per the requirement, as per, because every network has a different requirement and they can tweak these values so that that's optimal for that network. So this is just an example that if you are having, if you need a 100 gig payload, you just need the default modulation is BPSK, and default the baud rate is 69.4350, and default bits per second is 1. Similarly, if you want to increase, you can increase the trunk payload from 100 gig to 600 gig. And if you want more trunk payload, your modulation format, the default modulation format will change. It will go from BPSK till 64 QAM, and you have the hybrid modulation as well for sub 50 gig configurations. This is the capacity modulation and distance graph for the NCS 1004. So you can see that if on the x-axis you have the capacity which is in TBPS, and on the y-axis you have the maximum distance which we can cover using the NCS 1004. So if you are to the higher modulation formats, then your capacity is increasing but your distance is reducing. What it means is you can use, the application differs. So what it means is the you can use it for different application, like the 64 QAM you can use it for shorter distance, for example DCI. But the this BPSK, you will have a higher capacity, so you can use it for subsea application, so that you will get a higher you can cover more distance. Yeah. So it says DCI application where you can achieve 600 gig over 100 kilometer, and you have the subsea where you will get 200 gig over the 10,000 kilometers. So always there is a trade-off between your capacity, distance, bandwidth, all those things. So depending on what applications, for what application you need the box, you can tweak different parameters and you can use it. Now, what are the advantages of using the 1000 NCS 1004 over the competitors? So, we have the different boxes from Sienna, Infinera, Nokia, but how NCS 1004 is making the difference is it provides granular baud rate. So, as I told you earlier, the baud rate can be changed from 40 gig to 72 gig, and as well as the bits per symbol that can also be changed from 2 bits per symbol to 12 bits per symbol. Since this fine tuning is available here, it's a big advantage for NCS 1004, so that we can work it in a different segment of the network. It can work in a different segment of the network, and it will also reduce the cost per bit, which is very important in submarine application, because in submarine application there will be many vendors would be there, but whosoever will give the lowest cost per bit, highest spectral efficiency, that will win that game. So, so this is one of the advantage of NCS 1004. The second point is the time hybrid modulation is possible. As I told before, you can use different modulation format with time hybrid fashion as well. So what it allows is it allows for continuous control of spectral efficiency, and and in this also transmit signal shaping and nonlinear equalization is allowed. So these are the different advantages of using the NCS 1004. Now coming to the use case, where NCS 1004 is highly deployed currently, it's Google is our prime customer for this, where they are using it in the Curie subsea cable with the Bosog NCS 1004. So this giving an introduction of this Curie subsea cable. It's a 10,500 kilometer long cable from Los Angeles to your Valparaiso in Chile. So in this, mostly they are using from day one. They are using Cisco NCS 1004. As you can see, around 85% shares we have using the NCS 1004, and it's the first ever DCI box in the Google Subsea network, and it's deployed in the open config fashion. And this is not only the use case in the subsea cable in the Google Curie, but we have some other cables as well, where Cisco, along with other vendors, they have deployed NCS 1004. So we have other cables like Indigo, that is a cable in Singapore, and Maria, that's another cable that is from your USA, California, Los Angeles to Bilbao, Spain. So there also Cisco NCS 1004 Boshog is deployed, and it's being used. So these are different use cases with NCS 1004. Uh, so that's all actually I have. It's ended before time. So if there are any questions, then let me know.
So, folks, you can unmute yourself if any question you can ask. Okay. So, if no question, I think we are done here. Thanks, Nikhilesh. Yeah.
Thank you everyone for joining. I hope it was helpful. Yeah,
Thank you. We are closing now.
thank you. Yeah.
Nikhilesh.